function in R. And this is going to be a foundation lecture, so it's just about some basic functions that we are going to be looking at. This is going to be the outline, how to use R to compute some basic functions like area of a circle, volume of a cylinder, sum and product of a set of numbers, count of even and odd numbers, count of prime numbers, and factors of a number. So to begin with, let's first look at how the syntax or the pseudocode of writing function R looks like. This is basically the way it's going to be like, where we have the name. Every function has a name, so you have to give a name of the function. Then we have, within this parenthesis, we have the input, and within this space is your working space, or where the computation is going to take place in order to display the output. The last line within this will always display the output. So let's start with our first bulletin, which is the area of a circle. So when it comes to area of a circle, one thing about functions, creating a function, is that you have to always know the algorithm or the theory of what you want to create. So to get an area of a circle, we need pi radius square, and pi is constant, radius is going to be the input. So once we know this, we are good to go. So let's do this in R. So I'm gonna name it area of a circle. I'm going to name it area.circle. That's the name I'm giving to it. You can give it a different name. Then within this parenthesis, that's going to be the input. I just need radius. Once I know the radius, I'm going to get the area of a circle. So it's giving us pi times radius squared. Display A. If I ignore this and I run it, I'll not be able to get output. So I have to bring A so that it can display the results. Someone may prefer to use print A or return A. I think we'll get the same result. So I prefer to use A. And also with the assignment operator, I prefer to use the equality sign as opposed to using this as my equality sign. Someone may prefer to use this, someone may prefer to use the equality sign. I want to go with the equality sign as my assignment operator. So let's run this. Then let's call our function area.circle. So we have it there. Then let's use a radius of 3 and see the results. So I'm going to highlight that and run. So that's the result as is being displayed. Now suppose you have many radius, like we have radius 1, radius 2, radius 3. We want to see the result at the same time. The sapply function is good to use. So 1 to 5. Then my function comes, which is area.circle. So I have area.circ. So let's run this. So I think it's taking time. It will okay, so now that's the results. So for when the radius is 1, this is basically going to be the answer. When the radius is 2, you're going to have this. When the radius is 3, you're going to have this. And you can see this is similar to what we have as in our previous computation. So we are done with area of a circle in R. Let's look at the next function. How do we get the volume of a cylinder in R? So the syntax or the algorithm is given as that pi radius square height, right? Once we know this theory, we know this principle behind the volume of a cylinder, we are good to go. But here we have two inputs. We need the radius and the height. So let's do this in R. So I'm gonna get volume of cylinder. So I'm gonna have volume dot cell. This is the name I'm giving to it. Then I need radius and I need height. H for height, R for radius. So the volume is actually given as pi times radius squared times height. Then display V pi radius square height. So we are good to go. So let's assume we have radius to be 2 and our height is 3. Let's look at the results. So I'm gonna highlight this and run. So that's the results. You can decide to change it, make R3 and radius, make radius 3, make height 2 to see different kind of result that you're gonna get. So let's look at the next example. Sum and product of a set of numbers. How do we get, if we have a set of this form, how do we get a sum? Computationally, manually, this is how you're gonna get it. You just have to sum each of the elements and the result is 13. How do we do this in R? So sum of element in a set. So yeah, our set is Z and we have 3 minus 4. 3 minus 4, we have 5, 8, 1, 5, 8, 1, and we also have minus 7, 3, and 4. So these are set. So let's run this. I'm using Ctrl Enter to run it instead of using the run button here. Run. So how do we get the pseudocode for sum? I'm going to name it sum.function, sum f. Then within this, I'm going to my set. I'm just using x as the input. So you know, because this we are dealing with a vector, we have to ensure that we use some mathematical principle. You know, with addition, one of its identity or one of its properties is an identity. Its identity property is that if we add any number to 1, if we add any number to 0 instead, we are going to get the same number. That is one of its identity property that it has. And because we are dealing with summation, we are supposed to incorporate that in this pseudocode. So first of all, we have to get that counter 0. So that's my counter to help us get the identity property of addition. right? So I'm going to use the for loop. The for loop is suitable for vectors, right? So for I in 1 to 1, for each index, the I is basically the index, right? So I is equal to index, my x is equal to set. So x is set, I is index. So for I in x, we want to sum all the elements in the set. So k should be equal to k plus I. Then display k for us. So with this, we are gonna get the sum of the function that we are actually looking for, and we'll compare it with the inbuilt function sum to see if we are going to get the same result. So let's run this. Then let's run the function with our set z. So the name of the function then z. So we have 13 as compared to the manual one. Also, if you use the input function, we are going to get the same results as 13. So what about the product? So here we are done with the sum. What of the product? We know the product is supposed to multiply each element in that order, starting from the first index, second, multiply in that order to get this result. So how do we do this in R? So product, let me copy the same code in here. Just paste. So we have product of element in a set. So the same set, but here I'm supposed to use the multiplication identity, which is if you multiply any number by 1, you are going to get the same number, right? That's the multiplication identity. So that's going to be my counter for the product. Then I think I'm good to go. So I'm going to change the sum to product, PROD is going to be my product. I think we are good to go. So it's for the same syntax, and because we are dealing with multiplication, you're supposed to change this to multiplication sign as usual, so that it can give us the result that we are actually looking for. So I'm gonna run this, the whole of this product of z. So if I run that, I'm getting the result that is similar, and I can use the input function to get the same result. Right, I'm getting the same result as the manual one. Now the next example is count of even and odd numbers in R. How do we get a count of even and odd numbers in R? So let's do this. So count of even and odd numbers. So I'm gonna, because I want to get the two results at the same time, I'm gonna use odd dot even count. This is the name of the function that I'm gonna use. Okay, let's do it one after the other, then I'll combine it. Right, so let's start with odd count. I want to count the number of odd integers. I'm using the same um, set z. So the function so x is my set. I have to get a counter for it, so I'm using k as my counter. So I'm naming it KO, counter for odd numbers. So counter for odd number. So I'm going to use the for loop because I'm still dealing with a vector. So for I, that's the index in 1 to the length. Here I'm going to use the length of the set that I'm dealing with, because I want to count for each of these elements in the set. I want to count which one of them falls under or is an odd number. So I'm using the length. So for I in 1 to the length of the set, if xi, that is if each of the index, if each of the element in the set, for instance it starts with 3, if 3 mod 2 is not equal to 0, right, then we know that it's going to be an odd number. We are basically using what do we call it, this kind of algorithm. We know that for even numbers, there are numbers that can easily be divided by 2, and with odd numbers is the vice versa for odd numbers. Or even numbers are those numbers when divided by 2 has a remainder of 0, and the opposite is for odd numbers. So that's the logic that we are basically using. So for even numbers, for each of the element mod 2, we are going to get 0, and for odd numbers, for each of the element mod 2, we are going to get 1. So I have for I in 1 to the length of x, if xi, that is if each of the element mod 2 is not equal to 0, then we want it to count it as an odd number. So plus 1 count as odd number, right? Then we want to display that odd number, KO. So let me name it odd.num. Print this. So let's run this and see what we're gonna get. So let's call our function odd count, odd.count, and my set is z. So I'm gonna run this. I'm gonna run this. Oh, there seems to be a mistake here. Okay, let's look at it. let's run it again and see the results. So let's see if the odd numbers are really 5. We have this. Let's go back to this place. So we know those numbers that can easily divide by 2 with a remainder of 1, or the remainder is not equal to 0. Any of them works. So this divide 2, we know there is going to be a remainder of 1. 5 mod 2 is going to be a remainder of 1, so it's going to count as a second index. This mode is going 3, 4 and 5 here, so we have 5 of them being as odd numbers, right? So what of even? So I'm gonna copy the same thing and just change 1 or 2 things, and I'll get that for even. So for even, count of even, then the first one will be odd. Count of odd. So count of even numbers, here I'm gonna use the counter k for the even. So for I in 1 to the length of the set, if each index mod 2 is 0, that is if the remainder is 0, then basically it qualifies as an even number from our basic concept in mathematics. Any number that divides 2 exactly will be classified with a remainder of 0 will be classified as what, an even number, and we know that from at the basic level, right? So I'm gonna change this to k and this to ke because I'm using even. So I think we should be good to go. So instead of odd count, I'm gonna make it even count. Even dot count, right? Now I'm gonna run this. I'm gonna run this, and let's see the result. Oh, I'm supposed to change this to e. Yep. So let's run it again. Yes, and we have 3. And let's look at it. Yes, I think this divides 2. The remainder is actually going to be 0. Divides 2, 8, going to be 0, and the last is 4. Divides 2, the remainder is 0. So that's it. So we are good to go. Now I wanted to add this. How do we then see the element? How do we see the element? So it has given us 3, but how do we know which of the 3? Is it talking about is the 3 talking about just how do we know the element? How do we get a set of elements that are even? How do we get a set of elements that are odd? So I want to add this to, I'm gonna combine it. So I'm gonna name it even and odd numbers. So I'm gonna list of even and odd numbers, right? So basically I can use the same pseudocode, but I'm gonna change 1 or 2 things, so you have to pay attention to it. So I'm gonna name it list odd dot even underscore list. Right, so this is my function. So set x is still going to be my set. Then yeah, I'm gonna have counter for odd. Sorry, this is supposed to be even. Counter for even. Then I'm gonna get a counter for odd. So counter for odd number. Counter for odd number. We are basically using the identity property of an addition, so that it can count the element that is of interest to us. So for I in 1 to the length of x, if each of these elements mode 2 is equal to 0, then it's to count it as what? Even for us, right? So count as even. So I'm gonna change the first one, count as even. Count even. So count as even number, right? That's the first if statement. If this, then it should give us that, right? If, but instead of even using the counter, because you want to get a list of numbers, we are supposed to create a container instead. So I'm going to use this for the container. For the container, yeah. So container for even, then container for odd. So I'm going to get a container in which I want to get a list of even and list of odd. So from here, if this condition hold, if the index that's an element mode 2 within the set is equal to 0, then we want it to be considered or to be chosen as our even number. So I'm going to change it. We want to put in a container, so it should be classified as an even number. So I'm still using the KE. That's the counter for the container for even. So the index, that particular index, for instance, it picks 3 mode 2 will never give you 0, but if you pick 4 minus 4 mode 2 is going to give you 0, right? So it's going to pick this particular index, right, and place it inside this container that we have. That's basically what it's going to do, or that's how this line of code is going to work. So store index as an even number, else if this statement changes, else if x, that's if x I, that's the index mode 2, is not equal to 0 or is equal to 1, whichever way you want to do it, is not equal to 0 by using this, or you can say it's equal to 1, right? Else if this condition holds, then it means that it is actually what's going to be classified as an odd number. So we're going to create a container in which it's supposed to move into. So as we did for the even, you're going to use the same strategy for the odd. So I'm going to copy and paste, store index as odd number. So yep. Then the final result, I want to get a list of the numbers, so I'm gonna use list. Then I have my odd dot num odd numbers. That should be ko. Then even dot num ke. So I think we are good to go. So the name of the function is actually going to be odd dot even underscore list, right? So let's run this. Let's run the whole of this line and see the results. So let's run. I hope it works. Yep. So we can see now the odd numbers is being listed and the even numbers is being listed. So previously we had 5 of the odd numbers and now we have 3 of the even numbers. So we are good to go. The next example is on prime numbers. How do we do this in R? So I'm still using the same set Z. We know prime numbers are basically numbers that have only 2 factors, so 1 and the number itself. So if you look at this, 3 is a number that has only 2 factors, 1 in itself, that's 3, 1 and 3. Negative numbers can never be classified as odd numbers, so we ignore that. 5 will to be classified as that. 8 has more than 2 factors, so it cannot be classified as a prime number. So basically we have 3, right? How do we do this in R? So I'm gonna do prime count, right? So I'm going to name it prime.count. So X is going to be my set. So we still have to get a counter for prime. So I'm using K as a prime, the counter, because of the identity property, right? We want it to count the number of prime for us, so I have to use a counter, the identity property, right, for addition. So I have the counter. I'm going to use the for loop because I'm going to have a set. I'm going to use the same set Z. I'm using the same set. So for an index I in 1 to the length of my set X, because with prime numbers you have to be very careful. 2 is the only even prime number, so you have to be specific with it. For 2, for I in if the index that we have is actually equal to 2, then we have to count it as count it as a prime number, because it's one of the only even prime number that we have, so we have to be specific with it in our serial code. So count as a prime number. Right. Once the index it goes through the set and that particular element within the set is 2, it classifies as what? A prime number. Else, if any of this index mode 2 to that index, when we subtract 1 from that index and is actually equal to 0, if this condition holds, we don't expect it to count as a prime number. Else, it should be counted as a prime number. So let me copy what I have here. Count as a prime number, right? Then should display the list of prime numbers for us. So let me see. I think we are good to go. Let's highlight and run. So let's call the function prime dot count, which is we are still using the same set z. So it's 3 as we have here, right? So I think we are good to go now. The last but not the least is, how do we get factors of a number for a given number? For instance, we have a number 15. How do we get the factors? We know factors of a number are those numbers that can equally divide that particular or that given number without any remainder, right? So if you pick 15, these are the only set of numbers that can divide 15 without a remainder. So these are basically the factors of n, which is 15, right? So let's do this in R. So factors of a number, or devices, factors of a number. So I'm going to name it fact dot n. Fact dot num. That's the name of the function. I'm gonna use the same or set, which is z. I'm gonna use the same set. Okay, I'm not even this has got to do with, so let me use n15. Let me use this because we're not dealing with a set. So function x for the number. So here x is the given number. So x is the given number. I'm still supposed to make use of the for loop. So for I in 1 to the number that I'm going to deal with. So if it's 15, we're actually looking at 1 to 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 numbers. Which of these numbers are factors? So if x, that's the number, mod I, which is basically the index within the number, right? So 1 to 15. If we pick any of these numbers from 1 to 15, if we take the mode of it, 15 mode this particular number, and the result is actually 0, that's it, it is 0, then we want it to print that particular element for us. That particular element is of interest, and that's going to give us the factors. So let's run this. So fact.num. So my n is now 15, so I'm gonna use n of 15. So let's run this. So that's the list of numbers that devise n without any remainder, and these are the factors of a number.